Okay, so when we last left off, we were doing a series of examples on balancing redox reactions under acidic and basic conditions. So now I'd like you to take a look at the following example, and I'd like you to balance the following reaction under basic conditions. So let's take about 3 to 4 minutes and we'll cover the first half reaction involving chromium 3 oxide. And then after another 4 minutes, we'll cover the second half reaction and show how to put the half reactions together to generate your overall balanced redox reaction. So let's start off with writing out the first half reaction for this redox equation, and we'll discuss in about another 4 minutes. And if you have any questions, don't be shy to message your questions in the chat. And I'd like to see your proposed balanced half reaction in the chat for the first half reaction involving chromium 3 oxide. And we'll resume our discussion and we'll discuss this first half reaction in about another 2 to 3 minutes. And again, if you could message the proposed half reaction involving chromium 3 oxide in the chat or using the annotate feature, we'll discuss in about another minute the first half reaction. Okay, so let's discuss. So first and foremost, let's write out all of the chemical species that contain chromium. Next, what we're going to do is we're going to assign oxidation numbers. So what is the oxidation number of chromium in the following compound? What is the oxidation number of chromium in the following chromium oxide? What is the oxidation number? 3, yep, plus 3, yep. What is the oxidation number of chromium in chromate? Well, solving for that, we get the oxidation number of oxygen times the number of oxygen atoms minus the total charge over the number of chromium atoms. That gives us plus 6. So our change in oxidation number is 6 minus 3. So that gives us 3 electrons lost per chromium times 1 chromium atom. That in turn gives us 3 electrons lost. So we put 3 electrons on the right. Now what we have to do is we have to look at our chemical equation in a little bit more detail. And we have to look and see, so we have 3 oxygens on the left We have 4 oxygens on the right. So to balance oxygen, what do we add? What do we add to get that 1 additional oxygen on the left? What do we need to add? Under basic conditions, how do we add 1 oxygen to the left-hand side? So if we want 1 oxygen to the left, yes, you will have to add hydroxide in some form, but remember how I provided you a cheat sheet? If you want to add 1 oxygen to the left, you add 2 hydroxide to the left and 1 water to the right. So if we combine our equations together, we get Cr2O3 plus 2OH minus leads to CrO4 2 minus plus H2O plus 3 electrons. So this would be our oxidation half reaction. And I'd like you now to try to write out a balanced equation for our reduction half reaction. And we'll discuss the balanced reduction half reaction in about 3 to 4 minutes. Yes, we'll discuss this. We'll discuss that component actually. So looking at this equation, as we notice, chromium is not fully balanced. So what we're going to do is we're going to adjust the coefficient of chromium. Okay, so now we have 8 oxygen atoms. We need to adjust our electron counting because we now have 2 chromium atoms. That gives us 6 electrons lost. Now that we have 8 oxygens on the right and 3 on the left, we need to add a total of 5 oxygens to the left. So we multiply this expression by 5, and that gives us 10 hydroxide and 5 water, leading to 6 electrons lost total. So here's our complete and balanced oxidation half reaction, accounting for the fact that we have 2 chromium atoms undergoing that change. So here's our complete oxidation half reaction under basic conditions. Let's now take about 3 to 4 minutes and try to write out a balanced reduction half reaction under basic conditions. And the response I see in the chat for the balanced reduction half reaction looks great so far. And we'll discuss this example in about another 2 to 3 minutes. And we'll discuss this example in about another 1 to 2 minutes. So let's discuss this example. So first and foremost, we have hypochlorite going to chloride. So first and foremost, we have the same number of chlorine atoms on each side. In hypochlorite, chlorine has a +1 oxidation number. In chloride, it has a -1 oxidation number. So then, if we look at the delta, we have -1 - 1. So we have 2 electrons gained per chlorine atom. And we have 1 chlorine atom undergoing a change. So we have 2 electrons gained. Okay. Now looking, we have 1 oxygen on the left. And in order to add 1 oxygen to the right, we'll look at our cheat sheet and we'll add a pair of water and hydroxide. Combining our equations together, we get 2 electrons plus ClO minus plus H2O leads to 2 OH minus plus Cl minus. Okay, now that we have both of our half reactions in hand, let's write out both of our half reactions. Okay, and now what we can do is we can multiply both of our half reactions in order to balance our electrons. So what should I multiply my top half reaction by to get 6 electrons in each of my half reactions? What should I multiply my top half reaction by? Wait, 2 times what would give me 6? What should I multiply this top reaction by? 3. So then, rewriting, we have 6 electrons plus 3 ClO minus plus 3 H2O leads to 6 hydroxide plus 6 chloride. Our electrons cancel. We cancel 6 hydroxide from each side. We cancel water from each side. That gives us chromium 3 oxide plus 3 hypochlorite plus 4 hydroxide leads to 2 chromate plus 6 chloride plus 2 water. So here we have our complete and balanced oh, that should be a 3. Just checking. Perfect. So now let's take a look and let's just verify really quickly, is this equation balanced? Is this equation balanced? Okay, so let's just put a check mark. Always make sure to do that last check. It's how you can catch any multiplication errors or any subtle errors when working through these redox balancing problems. Any questions on this example? If not, let's look at the following problem where we're asked to balance the following reaction under acidic conditions. So nitric acid is known as an oxidizing acid as it can participate in redox reactions. So I'd like you to take a few minutes and try to write out the half reaction involving copper solid. And really try to think about half reactions in terms of net ionic equations. And we'll discuss this first half reaction as it's somewhat straightforward in about 2 to 3 minutes. And don't be shy to message me your proposed half reaction involving copper in the chat or using the annotate feature. And we'll discuss this first half reaction in about another minute to minute and a half. Okay, so let's look. So we have copper solid going to copper 2 plus aqueous. So we went from copper 0 to copper plus 2. So our delta is 2 minus 0. So we have 2 electrons lost per copper times 1 copper atom. That gives us 2 electrons lost. Okay, so there's our first half reaction. Now I'd like you to take about another 3 minutes and try to write the half reaction for nitrate. So we have our oxidation half reaction. Now let's figure out our reduction half reaction. So let's try to work on writing out our reduction half reaction for the reduction of nitrate. And we'll review the second half reaction in about 3 to 4 minutes. And don't be shy to message me or unmute and ask any questions that you have verbally. And I'd love to see some proposed responses in the chat. And we'll discuss in about another 2.5 minutes. Let's try to get a few more responses in the chat. Practice really does make perfect for these balancing redox equations. And if you get the half reactions correct, you're almost all the way there to completing the problem. And we'll discuss in about another minute and a half. Okay, so let's discuss this example. So looking at nitric acid, HNO3, leading to NO2 gas. My question to all of you is, what is the oxidation number of nitrogen in nitric acid? What is the oxidation number of nitrogen in nitric acid? +5, yep. Okay, what is the oxidation number of nitrogen in nitrogen dioxide? +2 is close, but just remember to account for the fact that oxygen has a -2 preferred oxidation number, so nitrogen would be +4. So just to show the work for that, for nitric acid, we have -2 times 3 for oxygen, +1 for hydrogen, over 1 nitrogen atom, which gives us +5. For nitrogen dioxide, we have -2 for oxygen times 2 over 1 nitrogen atom, which is +4. So now we've checked, we have the same number of nitrogen atoms on each side. Our delta is 4 minus 5, which gives us -1, which indicates that we have 1 electron gained per nitrogen times 1 nitrogen atom. And that in turn gives us a delta of 1 electron. So we gained 1 electron. Now we have to focus on balancing this equation. So we have 1 hydrogen and 3 oxygens. On the left, we have 2 oxygens on the right. We need 1 additional oxygen on the right first and foremost. So what do we add? If we want to add oxygen under acidic conditions, what do we add? What do we add under acidic conditions if we want to add oxygen? We add water. In this case, we add 1 water. So now we have 1 oxygen and 2 hydrogens. So looking at our difference, we need 1 additional hydrogen. And how do we add hydrogen under acidic conditions? What do we add? H+. Okay, perfect. So let's now write out our equation. So we have copper solid leads to copper 2+ aqueous plus 2 electrons. And then we have H+ plus 1 electron plus HNO3 leads to NO2 gas plus H2O. Okay. Now what do I need to multiply my bottom equation by in order to balance my electrons? What number do I need to multiply my bottom equation by to balance the electrons? 2, yep. Okay, so I'm just gonna rewrite my equations just so that way there's no confusion as to where each of these numbers are coming from. 2H plus 2 electrons plus 2, HNO3 leads to 2 NO2 plus 2 H2O. The reason why we don't take into account the copper nitrate and the nitrate is the fact that for redox reactions, you only really care about the net ionic equation. If the nitrate isn't undergoing a change in oxidation number, and it's not undergoing a change or participating in the chemical reaction, then in the net ionic equation, the nitrate won't be present. It will cancel out from each side. We can have the nitrate, but in terms of balancing half reactions, you really want to look at half reactions from the perspective of net ionic equations whenever possible. Otherwise, you end up in a situation where you have nitrate and the nitrate is both participating as an oxidizing agent and it's also a spectator ion in some of the half reactions. Okay, so looking at the following chemical equation, we have 2 electrons on each side, so those electrons cancel. And then we get the so 2 electrons cancel, and now we get the following balanced chemical equation. One moment, allow me 1 second just to reset OneNote. So combining these equations together, we get the following overall balanced redox reaction. Now I'd like you to check, looking at this equation, is this equation balanced? Is this equation balanced? Perfect. So we put a check. Okay. So now let's move on and switch gears and talk a little bit about classifying reactions. So we're going to learn about common types of chemical reactions, and this will help you predict the products of chemical reactions that you see a lot in general chemistry. So first and foremost, the one major superclass of reaction is the decomposition reaction, where we have a compound reacting to give one or more elements or compounds. So a classic example of this is that carbonate salts will decompose to yield a metal oxide and carbon dioxide. So for example, if you take calcium carbonate and heat it, so we have our metal carbonate, we in turn generate our metal oxide and carbon dioxide. To add another example, if we have sodium carbonate, we in turn would generate carbon dioxide gas. And what other product? What is our metal oxide in this case? What is our metal oxide in this case? So sodium carbonate reacts to generate carbon dioxide and what metal oxide? What would the metal oxide be if we have sodium carbonate? What is our metal? Sodium, yep. So we generate sodium oxide. In a similar vein, hydroxides will decompose to yield a metal oxide and water. So for example, calcium hydroxide decomposes into calcium oxide and water. Let's look, if we have, for example, aluminum hydroxide, what products will we get? So from aluminum hydroxide, what will we generate?
Aluminum oxide?
Yep, exactly right. So we take aluminum 3+ and O2- and cross our charges. That gives us Al2O3. And we also generate water. So for this equation, we're just going to need to balance it really quickly by adjusting some of the coefficients. It's nothing that we can't do. So let's just quickly adjust our coefficients. So 2 and 3. So this is another example of the decomposition of a metal hydroxide to yield a metal oxide and water. Finally, let's look at another decomposition reaction. Let's look at another decomposition reaction that we've already seen. Carbonic acid decomposes to yield water and carbon dioxide, where this H2CO3 is carbonic acid. Another decomposition reaction related to carbonic acid is that if we have sulfurous acid will decompose into water and sulfur dioxide. So these two reactions are mechanistically very similar. Now, one thing I want to emphasize is that many reactions, such as decomposition reactions, are also redox reactions. So for example, if you take a binary ionic compound, you can, under the correct reaction conditions, decompose the binary ionic compound to its component elements. So if we look at oxidation numbers here, in this following mercury oxide, we have an oxidation number of +2 on mercury and -2 on oxygen. In our product, we have pure elements, so both of our oxidation numbers are 0. So as we notice, in this reaction, is there a change in oxidation number? Is there a change in oxidation number? Do we have a transfer of electrons? Is there a change in oxidation number? Do we have a transfer of electrons? Yes, we clearly see there's a change in oxidation number, so this reaction is clearly a redox reaction. So to give another example of this kind of reaction, if we have sodium chloride, we can decompose sodium chloride under electrolysis to 2 sodium solid and chlorine gas. Again, this is a redox reaction because we're changing our oxidation state of each of our elements. Sodium is going from +1 to 0, and chloride is going from -1 to 0. Okay, another common decomposition reaction that we often see in the laboratory is that chlorates will decompose to yield a metal chloride and oxygen gas. So the most common example is that potassium chlorite decomposes to yield potassium chloride and oxygen gas. So this could be considered a gas forming reaction. So let's look at a variant for this reaction where we're looking at calcium chlorate leading to calcium chloride and oxygen gas. But before we do that, I just want to look at the oxidation numbers for this top reaction. So we have oxidation numbers of +1, -2, and +5. The +5 is for chlorine. In our product, the oxidation number of chlorine is -1. So chlorine has been reduced and oxygen went from -2 to 0. Oxygen was oxidized. So this chlorate decomposition is a clear example of a redox reaction. Okay, so now looking at this new example, if we wanted to balance the chemical equation, we have 6 oxygens on the left, we have 2 oxygens on the right. 2 times what would give us 6 oxygens? 2 times what would give us 6? 3. Yep, exactly right. So we need a coefficient of 3. And now, just checking, it looks like we have a balanced chemical equation. Perfect. So this is just another example of chlorate decomposition. Any questions so far on decomposition reactions? Okay. So let's talk about the other side of the coin of decomposition reactions, which are combination or synthesis reactions, which I like to think of as decomposition reactions in reverse. In a combination or synthesis reaction, we have the reaction of 2 or more elements and or compounds to give a single compound. So for example, a metal oxide and water combine to form a base. So this is why metal oxides are sometimes considered basic, as in water, they make a hydroxide. Let's look at an example, and let's look at this reaction. It's not a redox reaction. There's no change in oxidation number. So let's try to look and see, and let's look at examples of these kinds of combination reactions applied to different substrates. So if I combine sodium oxide and water, what product will I get? What product hydroxide will I get? Sodium hydroxide, yep. And balancing this equation, we generate 2 molecules of sodium hydroxide. So this is just another example of metal oxides reacting with water to generate basic metal hydroxides. Okay, so let's look at another example, this time with non-metal oxides. So if you have a non-metal oxide, they can combine with water to form an acid. That's why non-metal oxides are considered acidic. For example, carbon dioxide can react with water to make carbonic acid. Similarly, and this is one reaction you don't want to see up close, or you don't want to be anywhere near while the SO2 gas is reacting, is SO3 or sulfur trioxide gas. Sulfur trioxide can react with water in a combination reaction to generate what very famous acid? What acid can be generated as we react sulfur trioxide and water? Sulfuric acid, exactly right. In another example, nitrogen dioxide gas can react with water to generate what strong acid? One thing that you need to be careful of when predicting the formula is you need to make sure it's charge balanced. So our product would be nitric acid, and now we have to go through and we have to balance this equation with respect to hydrogen, nitrogen, and oxygen atoms. So looking at this equation, we have 2 hydrogens on the left, 1 hydrogen on the right. We have 1 nitrogen and 3 oxygen on the left. We have 3 oxygens and 1 nitrogen on the right. So what we're going to do now is we're going to modify and we're going to try to balance out our number of hydrogen atoms. So that gives us 2 nitric acid, which gives us 2H plus, 2 nitrogens and 6 oxygens. Okay. So we have 1 oxygen and 2 hydrogens. So we'll adjust the coefficient of 2 once again. So that gives us 2 nitrogens and 4 oxygens. Okay, so looking at this equation, we're still not fully balanced. We're still not fully balanced in this equation. So let's continue to adjust our coefficients. So nitrogen dioxide is a little bit of an exception in terms of how it behaves. So if you're wondering why the equation doesn't balance, as a byproduct from this reaction, we also get nitrogen monoxide. So this nitric acid generation from nitrogen dioxide is a bit of an exception. Just to round out our list, if we have sulfur dioxide reacting with water, we can generate hydrosulfuric acid. Nitric acid is a little bit weird because it often participates in redox reactions. Okay, so let's continue on and let's talk about combination reactions. Many combination reactions are redox reactions. So for example, we can take a metal and a non-metal and react them to form an ionic compound. So for example, aluminum and bromine react to make aluminum bromide. Likewise, for example, we can take, let's do calcium solid reacting with iodine solid. And what product would we get if we combine this metal, calcium, with this non-metal of iodine? What product will we get? What product will we get from this combination reaction? And then just remember to balance your charges. So we have calcium 2 plus, I minus, we cross our charges. That gives us calcium iodide solid. So our rules for writing out ionic compounds with the proper charge balance formulas still apply, but your logic is good so far. There are also some miscellaneous combination reactions, and these are primarily seen in organic chemistry. Okay, so let's continue on and let's talk about exchange reactions. So exchange reactions are reactions where the atoms, and I just want to put in parentheses here, or ions in 2 different compounds are exchanged to give 2 new compounds, okay? So AB plus CD leads to CB plus AD. So we essentially have swapped are atoms or ions. So we often see exchange reactions in the context of the exchange of cations or anions in two ionic compounds. A classic example of an exchange reaction is a precipitation reaction, where, for example, if we mix barium chloride and lead nitrate, we have exchanged in our products the barium and the lead atom. Likewise, acid-base reactions, when we talked about acid-base reactions, we can think of them as a variant on this exchange reaction pattern where the metal cation associated with the base is exchanged with the acid's H+ cation. So in this case, sodium and hydrogen are exchanged. Let's look at an example. For example, if we react sulfuric acid aqueous with let's do lithium hydroxide aqueous. We can think of it as the exchange of hydrogen and lithium, but you always have to go through and you have to write your formulas following the charge balance rules. So we get lithium sulfate and H2O, and then we can balance the equation once we have our skeletal equation created. Now, you can't, one thing I really want to emphasize, you can't just swap your atoms and call it a day. You need to make sure that the formulas that you're writing are charge balanced. Does that idea make sense so far? Does that idea make sense? Any questions so far on this section? Okay, so let's discuss another subclass of reaction, and this is really important in the context of redox reactions, and these are our single displacement reactions. They're a reaction where an element reacts with a compound to give a new compound and a new free element. So let's use some color coding for that. So we have our element reacting with a compound that in turn gives us a new compound and a new free element. So there are many different types of displacement reactions. The first of which is hydrogen displacement, which is displacement of H+ to produce hydrogen gas. One example of hydrogen displacement is if a metal reacts with water to give a base and hydrogen gas. So just to showcase what's going on here, we have our pure element metal, and it is displacing, it is replacing hydrogen in our chemical formula. So our metal is displacing hydrogen from water. So we go from our initial compound, water, to a new compound, which is our metal hydroxide, and we also generate a new free element. So in effect, our metal has replaced or displaced the element hydrogen. Let's look at another example of a hydrogen displacement. If we take calcium solid and we place it in water, what product will we get? What product hydroxide will we get?
Calcium hydroxide.
Exactly right. So we write out our formula of calcium 2 plus OH minus. We cross our charges. That gives us calcium hydroxide. Again, in a displacement reaction, our pure element replaces a pure element found in our compound. That in turn gives us a new compound and a new pure element. Now, we do have to balance this equation. So if we have 2 oxygens on the right, we need 2 oxygens on the left. And now it looks to me like this equation is balanced. Checking one more time. Yep, this equation looks balanced now. So remember, when you're predicting the products from reactions, first you write out the formulas, then you can balance the chemical equation with these formulas in hand. Does that make sense to everyone? So another subclass of hydrogen displacement is when a metal reacts with acid to give a salt and hydrogen gas. So in this case, our metal is replacing hydrogen from our acidic compound. So that in turn generates a new compound and a pure element, which is hydrogen gas. So for example, if you put zinc in hydrochloric acid, you'll get zinc chloride and hydrogen gas. Let's look at what happens if you take aluminum and react it with hydrochloric acid. What product would we expect if aluminum reacts with hydrochloric acid? What product would we expect to see? Aluminum chloride, that's exactly right. And again, we write out our charges, aluminum 3 plus, Cl minus, we cross our charges, that gives us AlCl3, aqueous, and hydrogen gas. Now that we have our skeletal equation established, we can now balance our equation by adjusting the coefficients. So again, you write out the skeleton of your equation and then you balance it. Okay. So let's look at a few other subclasses of displacement. In a metal displacement, we are, by definition, displacing a metal. This is displacement of a metal. So a metal reacts with a metal salt to give a new pure metal and a new metal salt. So in this case, our metal, that's our pure element, is displacing the metal in our ionic salt. So for example, if you react aluminum and iron 3 oxide, aluminum will displace iron and will generate a new compound, aluminum oxide, and a new pure element of iron. Another example of a metal displacement is that if you have, for example, lithium solid reacting with lead chloride, for example, what products would we expect to see? What product would we expect from this metal displacement?
Lithium chloride plus lead.
Right. So we have lithium plus Cl minus. We cross our charges. That gives us lithium chloride solid. And we also generate lead as a byproduct. Now we adjust our coefficients to balance chlorine and balance lithium. And now we have a complete balanced equation. Now, one thing that I want us to sort of pay attention to here, is this reaction a redox reaction? Is this reaction a redox reaction? Is this reaction a redox reaction? Yes, it is. We went from lithium 0 and lead +2 to lithium +1 and lead 0. So many of the displacement reactions that you see are redox reactions. Keep that in mind for later, okay? Now, another type of displacement is known as a halogen displacement. As its name implies, it involves a halogen, which is a group 7A element. In a halogen displacement, a nonmetal reacts with an ionic salt to generate a new pure nonmetal and a new ionic salt. For example, chlorine can displace bromine from potassium bromide to generate a new salt, potassium chloride, and a pure element of bromine. So another example of a halogen displacement, if you have chlorine gas and you're reacting it with, for example, potassium iodide, what product would we expect from this reaction?
Would it be potassium chloride?
Yep, exactly right. We get potassium chloride and iodine as our two products. Now we're ready to balance this equation with respect to chlorine and iodine. So we put our following coefficients, and now we have our balanced chemical equation. Let me just add one more state symbol just for completeness. Does this example make sense right now? Any questions on this example? Okay. So let's talk a little bit about, well, how do I actually predict whether a displacement reaction will occur? We've sort of been taking that at face value, but just like precipitation reactions, we actually have a series of tools to explain and predict when does a displacement reaction occur and when does it not occur. So the reduction activity series, which is this giant table below, it's a set of oxidation half reactions arranged from the strongest and most reactive reducing agent to the least reactive and the weakest reducing agent on the bottom. Okay, so here's our ranking. You don't have to memorize this. You will have to know, if I give you this activity series table, what to do with it.
It's a different solution too. Yeah.
Sorry, what was that? Did someone have a question? So looking at this activity series, it provides a ranking for the reactivity of different reducing agents. So you can also arrange atoms in terms of their reduction half reaction and their strength as oxidizing agents, although that's far less common. So in order to predict displacement reactions using the reduction activity series, in order to predict displacement reactions using the reduction activity series, first and foremost, we have to follow these sets of rules. First and foremost, if the neutral metal or non-metal anion on the left of the activity series is higher on the activity series than the metal ion on the right, then a reaction occurs and the neutral metal will displace our metal ion from the compound. Okay, so let's look at an example of this. So if we have zinc reacting with hydrochloric acid. So if we find zinc in the periodic table, zinc is our neutral metal on the left-hand side. If we compare that to our metal or hydrogen ion on the right-hand side, is zinc higher than hydrogen? Is zinc higher than hydrogen on the periodic table? Is zinc higher than hydrogen on the periodic table? Looking at this activity series, is zinc above hydrogen on this activity series?
Yes.
Yes. So then, because zinc is higher, a reaction does occur. So then, we see that a reaction occurs, and as a result, zinc will displace hydrogen from hydrochloric acid, giving us zinc chloride aqueous and hydrogen gas. Okay, so let's now talk a little bit about each of the components. And to answer the question in the chat, I'll check into that in one moment. So if the neutral metal or non-metal ion, is known as the reducing agent, and it's found on the left of the activity series. So for example, if we really break down this top reaction, zinc solid is going to zinc 2+. So this is an oxidation half reaction, and zinc is our reducing agent. It's donating electrons. Yep, so this is the chapter 7 notes, part 3, which are found on Canvas. So the metal ion, which is often a metal cation, H+ ion, or a neutral nonmetal, are going to serve as our oxidizing agent in these reactions, and they're found on the right of the activity series. So for example, in this case, we have H+ aqueous being reduced to hydrogen gas. So this is a reduction half reaction, and H+ is our oxidizing agent. So the activity series provides us a way of gauging whether or not a reaction occurs. And the way that it works is you compare the relative position of your reducing agent and your oxidizing agent on the activity series. If your reducing agent, which is your neutral metal, is above your oxidizing agent, which is your cation, H+ ion, or non-metal, a reaction occurs. So we're next going to look at a graphical method. And I like this method because it's very easy to directly use the activity series. So let's take a look first and foremost, we have to identify the neutral metal or non-metal anion. So what is our neutral metal or non-metal anion in this case? What is our neutral metal or non-metal anion in this case? Zinc, yep. So let's put a box around zinc. And what we're going to do is we're going to circle the neutral metal or non-metal anion on the left of our activity series. So I'm going to put a circle around zinc. Here's our activity series down below. Then you identify your metal cation, H plus ion, or your neutral non-metal. So what is our oxidizing agent? What is our oxidizing agent in this reaction? What is our oxidizing agent? What is our metal cation or H plus ion? What is it in this case? Looking at our chemical reaction, do we see anything that matches that description? Copper, yep, exactly right. So we put a box around copper and we're gonna circle copper, and this is copper 2 plus. So we're gonna circle our metal cation on the activity series. So I'm gonna circle copper. Okay, so now that we have this set up, what we're going to do is we're gonna draw an arrow. And you're going to draw an arrow from the metal on the left of the activity series to the metal cation on the right. Now, if the arrow is pointing down, so if the arrow is pointing down, a reaction occurs. If the arrow is pointing up, no reaction occurs. So then, looking at our reaction, if we have zinc, so if we have zinc reacting with copper chloride, is zinc above copper? As our arrow is pointing down, does an actual reaction occur? Following these rules, does an actual reaction occur? Yes, okay, so zinc is going to displace copper. That gives us zinc chloride aqueous and copper solid. So I really like the graphical method because you literally take the activity series, you draw on it, and it immediately tells you whether or not a reaction occurs in what I think is a pretty intuitive way. Does everyone understand how the graphical method works? Does everyone understand how the graphical method works? Okay, so let's work on, and let's look at another case. If the neutral metal is lower on the activity series, no reaction occurs. So let's look and let's try to see, does the following reaction occur? So we have iron, and that is going to be our metal, and chromium 3 plus, that's our metal ion. So I'm going to circle chromium 3 plus. I'm going to circle iron. So looking, if we draw our arrow is pointing up. So then does a reaction occur? If our arrow is pointing up, if our metal is lower on the activity series than our metal cation, does a reaction occur? Yes or no?
No.
No, we have no reaction. Perfect. So that's the graphical method in reading the activity series in a nutshell. Let's now try to apply what we've learned to the following example. So we're asked to predict the products of the following reaction and identify the oxidizing and reducing agents. And then we're asked to write a balanced molecular and net ionic equation. Okay, so now what I'm going to do is I'm just going to really quickly put a box around my neutral metal and a box around my metal cation. I'm going to go now to my activity series, and you may want to have that as a separate printout, whatever works best for you. So I'm going to go to my activity series. I'm going to find nickel and cobalt. So I'm going to circle cobalt, and I'm going to circle nickel, and then I'm going to draw my arrow from nickel to cobalt. And my question to all of you is, does a reaction occur between nickel and cobalt?
Yes.
Is the arrow going up or down?
Oh, no.
Yeah, the arrow is going up, so no reaction occurs. Sorry, one moment, I had it reversed. We have nickel 2+ as our, oops, let me just check this really quickly. So our cation is nickel 2+, and our neutral metal is cobalt. So if I circle cobalt and nickel 2+, and now I draw the arrow for the actual reaction that we're looking at, is our arrow pointing up or down? Is our arrow pointing up or down? Now that we've correctly identified our metal and our metal cation, is our arrow pointing up or down?
Down.
Down. So then if our arrow is pointing down, does a reaction occur?
Yes.
Yes. Okay, perfect. So we do have a reaction at play. So now cobalt displaces nickel. So we have cobalt 2+ and Cl-. We cross our charges. That gives us CoCl2 aqueous plus nickel solid. Now, if we want to break this down into half reactions, we have cobalt solid going to cobalt 2+ aqueous. We went from an oxidation number of 0 to +2, so we lost 2 electrons. Likewise, for nickel, we went from nickel 2+ aqueous to nickel solid. We went from +2 to 0, so we gained 2 electrons. And as we can clearly see, when we add these half reactions together, that gives us cobalt solid plus nickel 2+ aqueous leads to cobalt 2+ aqueous plus nickel solid. Now you may say, how did you get these equations so quickly? Well, the beautiful thing about the activity series, and one thing I want you to pay attention to really quickly, does the activity series give us the half reactions? Does the activity series give us the half reactions?
Yes.
Yes. So all we have to do when we're writing out oxidation reduction half reactions is read off the half reaction from our activity series. Not too bad, right? Certainly makes things a little bit easier. So the activity series is not only a tool for predicting reactions, but it also gives you a cheat sheet for writing out half reactions. So if you're feeling stuck, don't be shy to look it over. It doesn't have every single half reaction, but it has most of them. Okay, does this idea of reading the activity series make sense to everyone? Is everyone comfortable using the activity series? So in order to test our understanding, let's try to look at the following reaction. Let's try to predict the products, identify the oxidizing and reducing agents, and write a balanced equation if a reaction occurs. And we'll discuss in about 3 to 4 minutes. The changes were only made in the part 3 notes at 7.11 and beyond. Yeah, so just from the classifying reaction section and beyond. If you're following along from the part 3 notes. So let's spend about another 2 to 3 minutes on this example, and then we'll discuss. And we'll discuss this example in about another 1.5 to 2 minutes. And don't be shy to message me or propose responses for whether a reaction occurs, and if so, what mass of product is generated. And we'll discuss this example in about another minute. So let's discuss this example. So what is our neutral metal? So what is our neutral metal in this reaction? What is our neutral metal? Can I get some responses in the chat? What is our neutral metal?
Gold.
Gold, yeah. So let's put a box around gold. And then our cation in this case is going to be H+. Okay, so let's go and find gold and H+. So I'm going to circle H+. I'm going to circle gold. And now I'm going to draw my arrow. And my question to all of you is, does a reaction occur?
No.
Yes, you're correct. A reaction does not occur. Perfect. Gold is lower than H+, Gold is known as a quote unquote noble metal. So it's not particularly reactive with acid. So all you have to put for this reaction is no reaction. So just make sure you're not overcomplicating these displacement reaction prediction problems. Sometimes you'll just literally put no reaction, nothing happens. And for that, it's pretty straightforward. Let's do another example. Let's do another example where we're asked to look at the following reaction. I'd like you to predict the products of the following reaction, identify the oxidizing and reducing agents, and then write a balanced molecular and net ionic equation for this reaction. So let's take about another 3 to 4 minutes, and then we'll discuss. And don't be shy to message me your proposed responses for the chemical equation for this reaction and whether or not a reaction occurs. And we'll discuss this example in another approximately 2 minutes. So let's discuss this example. So I'm going to need everyone's help here. What is our neutral metal? What is our neutral metal? What is our neutral metal? And don't be shy to share your responses in the chat. What is our neutral metal? So what is the neutral metal species in this reaction? What is on the left-hand side of our activity series? Cadmium, yep. So let's put a box around cadmium. Our metal cation in this case is tin. So we go all the way up to our activity series. We find cadmium. Cadmium is not on this one, but we have another activity series to work with. So let's go to this third activity series reference. So I find cadmium. I'm going to put a circle around cadmium. Tin, 2+, I'll put a circle around tin. And now drawing our arrow from cadmium to tin, does a reaction occur? Looking at our activity series, does a reaction occur?
Yes.
Perfect, exactly right. So just note on an exam, I'll give you the exact activity series that you'll need to use. So don't stress about memorizing each one, but just know in the notes, I compiled them all together on that one page to make it easy. So a reaction occurs, cadmium does displace tin. So we have cadmium 2 plus and NO3 minus. We cross our charges, that gives us cadmium nitrate aqueous, and we get out tin solid as a byproduct. Now, looking at our half reaction, we go from cadmium solid to cadmium 2 plus aqueous. So how many electrons did we lose? How many electrons did we lose when we go from 0 to +2? Just to make sure you're comfortable counting. Yep, we have 2 electrons lost. Okay, now let's look at tin. We go from tin 2 plus aqueous to tin solid. We went from we went from +2. Let me change colors to make that easier. Went from +2 to 0. So how many electrons did we gain? How many electrons did we gain? 2. Yep. So if we add our equations together, that in turn gives us cadmium solid plus tin 2 plus aqueous leads to tin solid plus cadmium 2 plus aqueous. Any questions on this example? Any questions on this example? If not, let's continue on. So let's work through the following example, and I'd like you to predict whether or not a product is formed, and then predict the product of the reaction between magnesium and cobalt acetate. And don't be shy to message your proposed response for the balanced chemical equation for this reaction. And we'll discuss this example in about 3 minutes. And don't be shy to message your proposed balanced equation or proposed products expected for this reaction. And remember, you're going to want to continue to use the activity series that I provided in the earlier part of this note. and we'll discuss in about another minute to minute and a half. And if anyone has any questions, don't hesitate to unmute and ask your questions verbally or in the chat. Okay, so let's discuss this example. So magnesium is our neutral metal. Cobalt is our metal ion. So let's go up to our activity series. So magnesium, it's a very strong reducing agent. All the way up here, cobalt, it's low on the activity series. So if we draw an arrow, does a reaction occur between magnesium and cobalt? Is magnesium higher than cobalt 2+ on the periodic table? Is magnesium higher than cobalt 2+? Yes, it is. So a reaction does occur. Okay. So then magnesium will displace cobalt, and that gives us magnesium, whoops, this should be CO2, magnesium acetate, aqueous, and cobalt solid. Now, writing out our half reactions, we went from magnesium solid to magnesium 2+ aqueous. And as we went from 0 to +2, we lost 2 electrons. Magnesium was oxidized. And for cobalt, we went from cobalt 2+ aqueous to cobalt solid. In this case, cobalt gained 2 electrons as it went from +2 to 0. And as a result, it was reduced. We add our equations together, the electrons cancel, and we're left with magnesium solid plus cobalt 2+ leads to cobalt solid plus magnesium 2+. Do these examples using the activity series make sense to everyone? You will actually see the activity series again in General Chemistry 2 in the context of predicting electrochemical reactions. There's a little bit more nuance there as there's some concentration dependence, but the logic is the same for predicting electrochemical reactions compared to the activity series. Both are built on this concept known as reduction potential. So this skill will serve you well in later classes as well. I don't see any questions in the chat, so let's keep going now. And this time let's do a guided example. So we're asked to predict the products of each chemical reaction, write a balanced chemical equation, and a net ionic equation for each reaction. Okay, so we're trying to read the following statement. So calcium is added to water. So we have calcium solid and water. Okay, what reaction springs to mind when you have this pure element, this pure metal and a compound? What type of reaction springs to mind almost immediately? What type of reaction does this remind everyone of? Where we have a metal and water, what do we call this kind of reaction? A metal and water, what kind of reaction is this? And don't be shy to unmute and submit your responses, or to submit your responses in the chat. What type of reaction occurs when we mix a metal and water? We discussed this earlier in this chapter. What do we call this kind of reaction? or let me rephrase to make it a little bit more straightforward. What element are we displacing? What element are we displacing? It's a hydrogen displacement, exactly. Calcium is displacing H plus from water, and in turn, we generate calcium hydroxide, calcium 2 plus OH minus, put a 2 here, and we generate hydrogen gas. Perfect. The total ionic equation is the same as the net ionic equation, so this first example is done. Let's look at the next example. We have a sample of zinc chloride added to magnesium. So we have magnesium solid, and for zinc chloride, we have zinc 2 plus and Cl minus. We cross our charges, that gives us zinc chloride aqueous. And now, what type of reaction is this? What type of reaction is this? What type of reaction is this? What do we think is being displaced in this reaction? Yep, it's a metal displacement. However, we can't just assume that this reaction occurs. We're going to check. So we're going to circle magnesium, circle zinc, and then we're going to go to our activity series. Don't forget to check in your activity series. So let's find magnesium, and once again we find magnesium, then we find zinc, and we draw our arrow. Is magnesium higher on the activity series compared to zinc? Is magnesium higher on the activity series compared to zinc? Yes, so then a reaction occurs. Don't omit that checking step. I'm taking the time to go to the activity series because you may get an example on the exam where it looks, or on later exams, where it looks like a metal displacement, but then it's actually no reaction. Okay, so magnesium displaces zinc. We have magnesium 2 plus, Cl minus. So we generate magnesium chloride, aqueous, and zinc solid. Wonderful. Now, looking at our net ionic equation, we can dissociate each of our soluble ionic compounds, strong acids and strong bases, into their component ions. And then all we have to do now is cancel our spectator ions. And that gives us, as a net ionic equation, magnesium solid plus zinc 2 plus. Whoops. Leads to magnesium 2 plus plus zinc solid. And that's our complete net ionic equation. Is everyone feeling a little more comfortable with the mechanics of predicting reactions? Okay, so let's look at the following two reactions. And given the word equations, I'd like you to predict the products of each reaction and write a balanced chemical and net ionic equation. So let's look at the following two reactions, and I'd like you to take about 4 minutes, 4 to 5 minutes, and try to write out a complete chemical equation for each of these two reactions if a reaction occurs. Keyword, if a reaction occurs. So remember to use your activity series, and we'll discuss this example in about 5 minutes. Don't be shy to message your proposed responses for each of the equations in the chat, or to ask any questions, or unmute and ask your questions verbally in the chat. And we'll discuss in about 5 minutes. Would anyone like to propose an equation or balanced equation for any of these examples? Or at least would anyone like to comment on whether any of these reactions, such as in equation 3 or 4, occur or do not occur? Does a reaction actually happen in both of these questions? We'll discuss this example in about another 3 minutes. And the comment in the chat is correct, yes. So if the neutral metal is higher than your ion, and the arrow is pointing down when you're using the graphical method on the activity series, then yes, a reaction will occur. That's exactly right. Mm-hmm. And we'll discuss this example in about another 2 minutes. And the responses I see in the chat for whether or not a reaction occurs in both of these examples look great so far. Now let's try to write equations based on that, and we'll discuss momentarily. And we'll discuss this example in another minute. And the proposed products that I see in the chat look great so far. So let's discuss this example. So first and foremost, we're going to write out our formulas. Iron is just Fe. Copper 2 sulfate, we have copper 2 plus, SO4 2 minus. We cross our charges, and that gives us CuSO4. Okay, so copper 2 plus is our cation. So if we go to our activity series, let's go to our activity series. So we have iron and copper 2 plus. Okay. So I'm going to circle iron. And then I'm going to circle copper. I draw my arrow. The arrow is pointing down. So does a reaction occur between iron and copper? Does a reaction occur? Just looking at this graphical method. Yep, a reaction occurs. Perfect. So then, let's predict the identity of our products. So iron will displace copper. So we have iron 2 plus, copper 2 plus. We cross, iron 2 plus and sulfate, which is SO4 2 minus. We cross our charges, and that gives us FeSO4, iron sulfate, which is aqueous. And as a byproduct, we get copper solid. If we want to write the net ionic equation, we dissociate all of our soluble ionic compounds, strong acids, and strong bases. And that gives us the following chemical equation. Then we cancel out all of our spectator ions, and that gives us the following net ionic equation. Now, a question that I have for the class is, looking at this next reaction where we have copper added to hydrochloric acid, I'd like some students in the chat to tell me, do you think a reaction occurs in this case? Do you think a reaction occurs in this case? If we mix copper and hydrochloric acid, do we expect a reaction to occur? Before we look at the activity series, do we suspect a reaction will occur? See, a lot of students that are skeptical that a reaction will occur. Let's see. You're not necessarily wrong. If we have copper and H plus, yes, the states are aqueous because it's a solution. Additionally, we know it's aqueous based on solubility rules. So remember, most sulfates are soluble except for a few exceptions. So the solubility rules will dictate what state symbol you put. Did that answer your question in the chat? Perfect. Okay. So let's go to the activity series and let's find copper and hydrogen. This example provides a pretty practical idea of the reason why copper pipes were relatively popular and the reason why even lead pipes were really popular. So let's circle copper. Copper pipes are often called corrosion resistant because if we compare copper and H+, our arrow is pointing up. Does a reaction occur between copper and an acid such as hydrochloric acid? does a reaction occur between copper and acid? If our arrow is pointing up, a reaction does not occur. Exactly. Copper is lower on the activity series than hydrogen, and as a result, copper cannot displace hydrogen. So then, all we have to do is put the symbol no reaction, or NR. Does that make sense to everyone so far? Any questions on this example? Okay, so let's continue on and let's look at the next class of reaction called the combustion reaction. So a combustion reaction involves a reaction. We have a compound containing mainly carbon, hydrogen, and nitrogen, though it can also have sulfur and oxygen. And the key feature of a combustion reaction is that we're reacting with oxygen gas to yield carbon dioxide and water as major products. So for example, combustion could be burning methane. We can also, for example, try to burn something like methanol in order to generate carbon dioxide and water. Allow me one moment just to balance this equation. Here we go. So we can also subject compounds containing oxygen to combustion, and those lead to pretty interesting problems. The key thing is we are producing carbon dioxide and water as our major products. We can also subject metals to combustion in that we can take magnesium and burn it in air to generate a metal oxide. So for example, if we take sodium metal and react it with oxygen gas, what product would we get from that reaction? If we burn sodium metal, what product, what metal oxide would we get out? What metal oxide product would we get out from reaction of sodium metal? Sodium oxide, which is Na plus O2 minus. We cross our charges. That gives us Na2O. Balancing this equation, we have coefficients of 2 and 4. Any questions on this example? Okay, now one critical thing that I want you to note. Just because a reaction makes carbon dioxide and water does not mean you have a combustion reaction. For example, the following reaction below is an acid-base reaction. It makes carbon dioxide and water, but it's not a combustion. We need oxygen gas for a combustion reaction. Does this example make sense? Does this idea make sense so far? So, we'll pause lecture at this time and we'll continue on our lecture and problem solving in laboratory.